Hello. In this video I'm going to be going through this problem here on electrostatics. Point charges Q and minus Q are located at the vertices of a square with diagonals 2L as shown in figure 3.1. Find the magnitude of the electric field strength at a point located symmetrically with respect to the vertices of the square at a distance x from its centre. Okay, so the first thing to understand about this question is the actual location of this point. So it tells us that this point is located symmetrically with respect to the vertices of the square. So that tells us that this point is not in the plane of this square. So we can imagine that it's coming out of the plane of the square, so maybe above it. And we know it is a distance of x from the centre of the square. So the first thing I'm going to do is draw a diagram to show more clearly the location of this point, and to do that I'm going to do it in 3D. So I've already drawn it here. So here you can see our original square with the 4 points located at the vertices. So I've done the plus Q charges in red here, and the minus Q charges in blue. And here is the centre of the square, and the diagonal of the square is equal to a length of 2L. And I'm showing the point where we need to work out the electric field strength from, which is a distance of x away from the centre of the square, and it's kind of above the centre of the square. Okay, so what I'm also going to draw on is the plane that is coming from the point where I need to calculate the electric field strength from. So I'll just draw that on. And you'll see in a moment why I'm drawing this plane on. So this is the point on this plane where we need to work out the electric field strength from. So the first thing I'm going to do is I'm only going to consider 2 of these 4 points, and I'm going to consider 2 diagonally opposite points. So I'm going to consider this plus Q charge here and this minus Q charge here, and you'll understand in a moment why I'm choosing 2 diagonally opposite points. So the field strength at this point is going to be a combination of the 4 electric field strengths of these 4 points. So I'm going to draw on the electric field caused by this point charge minus Q and this point charge plus Q. So for this minus Q point charge, the electric field is going to come away from this point like that, and so the arrow is going to be this way because this is a negative charge. And for this positive charge here, the electric field is going to go away from this point, so like that. And what we can now do is take components of these 2 electric fields, so like a vertical component and a horizontal component, but when I say horizontal I really mean a component that's in the plane in this plane here. So for this electric field, this blue one, its vertical component is going to be like this, coming down, and its other component, its horizontal component, is going to be along this plane here, like this. So these two are the components of this electric field here. And similarly, if I do the same for the positive charge's electric field, its vertical component is going to go upwards, and its other component on this plane is actually going to be in the same direction as this component. So it's in the same direction. So I draw it like that. So they're kind of on top of each other, but that's because they're in the same direction. And I'm just going to label these using the electric field. For the ones that are vertical, I'm going to call that like perpendicular to the plane, like that. And the ones that are along the plane, I'm going to call it parallel to the plane. So using the perpendicular and parallel signs. And the same for the positive charges. So this one is perpendicular to the plane, and this one, which is in the same direction as the negative charge, is parallel to the plane. Now, as soon as I've drawn this, you can see that the two vertical components, they actually cancel out, because they're in opposite directions, and they also have the same magnitude, because we know that the distance between each charge and this point here on this plane is the same distance. So the magnitudes of these two electric fields are actually the same, and so is the magnitudes of these two components as well. So the overall electric field, which is occurring as a result of these two charges, is just equal to these two components here added together. So they kind of add together and combine. So the overall electric field due to these two charges is just equal to 2E parallel. And yeah, so the reason I selected two diagonally opposite charges was so that I would get two components that are in opposite directions, so that they cancel out. So now I only have to consider these two components here. And I can do something similar for the other two charges that are diagonally opposite to each other. And I'm not going to draw them on, but you can see that the two components that we need to consider are just going to be in this direction, so perpendicular to these components here. And again, they are going to be in the same direction, so they will add up. And they have the same magnitude as these components, this E parallel. So overall, if I redraw this diagram with just considering this plane, the overall charge is going to look something like this. So if I draw the plane first, and I'll just draw on the diagonals just to find out where the centre is. so the overall electric field due to all four of these points is going to look like this. And you can see that they are in the same direction, so they add up. So I basically just have a 2e parallel in this direction and also a 2e parallel in this direction, and we know that they are perpendicular to each other. That's a right angle because that is a square. So all I need to know to calculate the overall field strength, electric field strength, so you can see from here that the resultant electric field strength is going to be equal to, so if I call that ER for E resultant, I know that that is going to be equal to 2E parallel, and I'm going to add on a radius vector, a unit vector to show the direction. So if I call this direction AX, unit vector, so this vector here plus this vector, so if I call that direction AY, so it would be 2E parallel AY, and that is equal to the resultant electric field that we need to calculate. So the magnitude of this electric field, we can see it's because it's a right angle triangle, it would just be equal to 2E parallel squared plus 2E parallel squared, and the square root of that because of Pythagoras' theorem, and so that is just equal to 8E parallel squared square root, which is equal to 2 root 2 E parallel. So all we need to know to calculate the resultant electric field is this value of E parallel, and we can do that easily if we come back to this diagram here. So we know that the electric field caused by any one of these points, if I call that E, I know that E is equal to Q, so one of the charges, over 4 pi epsilon naught r squared, where r is the distance between that charge and this point here. And the question tells us that the diagonals of the square are equal to 2L. So I know that this distance here, if I draw that on, that distance there is equal to L. And we want to work out what r is, the distance between the charge and the point here, so this distance here is r. And I also know that this distance here is x. So from Pythagoras' theorem I can write r squared is equal to x squared plus L squared. But we don't want to know E, this electric field here. We want to know E parallel, so a component of E. So if we call this angle here theta, and that angle is the same as this angle, this angle, so this one is 90 minus theta, minus theta, so it's this angle here, theta, and and that's the same as this angle theta here. And we can see from this triangle that cos theta is equal to L over R. So cos theta is equal to L over the square root of x squared plus L squared. And we know that E parallel is equal to E cos theta. So we can work out the value of E parallel now. So E parallel equals we can see that E parallel equals, if we just substitute in the value of cos theta into here, and you can see why it's why E parallel is equal to E cos theta, because this is E here, and you just have a triangle, and we want to work out this component. And so if we imagine that this is down here, we can see that this is just a right angled triangle. We know the hypotenuse, and we want to work out this component. So E parallel is equal to E cos theta, here the angle theta. So if we substitute in the value of cos theta into this equation, we get E parallel equals QL over 4 pi epsilon naught x squared plus L squared. It'll be to the power 3 over 2. So that's the value of E parallel, and we want to work out the resultant electric field. So if we just substitute this value of E parallel into here, so I'm going to substitute this value into there, then we get E resultant, the magnitude of that, is equal to QL over root 2 pi epsilon naught x squared plus L squared to the power 3 over 2. And yeah, that's the final answer.